Hello students, this is now Gauss theorem second application. We are calculating electric field due to a large sheet of uniform charge density. So here we are considering a sheet which is uniformly charged. As you can see, sheet has two faces, right side as well as left side. So we can have electric field along right side also as well as left side also. Now since we are applying Gauss theorem, so what we are required to do is we are required to consider a Gaussian surface which is going to enclose the charged sheet perfectly. So since the sheet is very large, so we are taking in a small scale. We are considering a small scale, and I am considering a cylindrical Gaussian surface here, which is shown in the diagram. Now, while applying Gauss theorem, as you know that it deals with the calculation of flux. So what I'm trying to do is in this particular cylinder is made up of three different surfaces. One is this, which is a circular disc, and a curved surface, right? So out of these surfaces, we are assuming small surfaces out here, ds2, ds1, ds1. Now electric field and ds1 are aligned in the same direction. Out here also they are in the same direction, but ds2 is at an angle of 90 degree with respect to electric field. So here I have assumed sigma be the surface charge density. Sigma can be calculated charge by area. Now we are applying Gauss theorem. E dot ds is equal to sigma a by epsilon naught. Now E dot ds plus E dot ds2 plus E dot ds3 is nothing but closed surface integral of E dot ds. Since we have three different surfaces, that's why I am splitting this integral into three parts, each involving ds1, ds2 and ds3. You can see from the diagram that ds1 is producing the flux. Why? Because electric field and ds1 are in the same direction. Electric field and ds2 are also in the same direction. So third one and the first one are giving you the flux. Second one is not providing the flux. Now if I consider A be the area of the sheet, I am considering A as the area of the sheet, and on integration of this particular area, it will be equal to A only. So I am assuming this face has an area of A only. This face is also having area of A. So if I integrate ds1, I will be getting A. Here also I will be getting A. So we are getting E dot ds1 as EA, E dot ds2 as 0, E dot ds3 as EA, sigma by epsilon naught. Simplifying this, we get E is equal to sigma by 2 epsilon. Now continuing with the second application, this is the third application which we assume, and this is we are required to calculate electric field due to two sheets. I am taking two sheets. Sheets are kept like this and like this. One is positively charged, other one is negatively charged. They are having same charge densities. We are assuming three different regions, region 1, region 2 and region 3. As you know that electric field produced by positive charge is always away from itself, negative charge is towards itself. You can see in region 1, E1 is the electric field produced by first sheet. So in this particular region, the direction of E1 will be away from the body, direction of E2, that is E2 is the electric field produced by negative sigma, so it will be towards the body. Similarly in region 2, electric field E2 is due to negative, which is towards the body. Electric field E1 is due to positive, which is again away from the body. So in this region, we can see that E2 and E1 are in the same direction. Similarly, in the third region, E1 and E2 are oppositely directed, right? So in region 1, since both are oppositely directed, so their values being E1 and E2 are being same, which we have calculated from application number 2. So we are getting electric field to be 0. In region 2, E1 and E2 again same, but they are added because they are in the same direction. This is the value. Region 3, E1 and E2 being same, they are to be subtracted. So we are getting this particular value. Hope you all have understood application 2 as well as application 3. Now I am moving to application number 4, which is electric field due to hollow sphere of uniform charge density. This is a sphere. It's a hollow sphere which is charged, right? We will be calculating electric field due to this particular surface inside, outside and on the surface. So I am calculating first outside. I am assuming distance r which is greater than radius of the sphere. So applying Gauss theorem, E dot ds is equal to total charge enclosed by the epsilon naught. So what is the value of total charge enclosed by the Gaussian surface? This is the Gaussian surface. Outside Gaussian surface is this one. So in the Gaussian surface we are assuming a very small area ds which is away from the body. Electric field is also away from the body, right? So we are getting E dot ds is equal to q by epsilon naught. E dot ds cos 0 degree, as I already explained, electric field and ds are in the same direction, so we are getting q by epsilon naught. E ds is equal to q by epsilon naught. Then E times integration of ds will be surface area of entire sphere, which we are getting 4 pi r square q by epsilon naught. So electric field is q by 4 pi epsilon naught r square. This is exactly equal to the electric field produced by single charge kept at the center. Okay. Now on calculating electric field on the surface, we are required to replace small r by capital R. Very simple. So we are getting E to be q by 4 pi epsilon naught capital R square. You can see that capital R is a constant, q is constant, 4 pi constant. This factor is a constant. But here in first case, q, 4 pi epsilon naught are constant, but r is a variable one. You have to remember this. Now we will be calculating inside, right? Inside, that is r is less than capital R. Here E dot ds is equal to q by epsilon naught, but the value of q is how much? 0. That's why electric field inside the body is 0. This you should remember, that in case of a hollow body, electric field inside the hollow part is always 0. We are plotting a graph here, electric field versus position graph. At center we are getting electric field to be 0, right? So as we move away from the center, the value of electric field is 0. Exactly at the surface, electric field is maximum, as I already explained here. And then beyond the surface, electric field starts decreasing at a rate of 1 by r square, which is shown here, right? This is application number 5. This is not so important for examination, but still you should learn this. In application number 5, we are calculating electric field due to solid sphere. So here we are required to consider volume charge density. Why volume charge density? Because charges are present within the body also. So here we are considering rho be the volume charge density. First we will be calculating outside the sphere, then on the surface, and then inside. Let's try to understand outside the sphere. For calculating outside the sphere, what we have done is we are drawing a Gaussian surface which is enclosing the charge perfectly. In this Gaussian surface, this is a very small area ds which is directed this side. Electric field is also this side. That means electric field and area are parallel to each other. Applying Gauss theorem, E dot ds is equal to q by epsilon naught. E ds is equal to q by epsilon naught. E ds, E is constant, taken ds only, integrating ds only, q by epsilon naught. Integration of ds will be 4 pi r square. So q by epsilon naught, the value is q by 4 pi epsilon naught r square. Here the electric field is only depending on r in this particular relation, right? Calculating on the surface, we will be replacing small r by capital R. Value will be E is equal to q by 4 pi epsilon naught r square. Like application number 4, this value is also constant. Now we are calculating inside the sphere, right? Inside the sphere means r is less than capital R. R is less than capital R. You can see this is the Gaussian surface. Smaller one is the Gaussian surface. Assuming a very small area here, area is directed this side, electric field is also directed this side. Here while calculating inside, E dot ds is equal to total charge enclosed by the closed surface divided by epsilon naught. What is the value of total charge? Is it q enclosed? No. Q is throughout the body, right? But we are assuming a very small part of the body. So I am assuming here q dash is the charge enclosed by Gaussian surface of radius small r. So what will be the value of q dash? Because we know the value of capital Q only, which is the total charge enclosed. But in third case, charge enclosed is not total, it is less than total. For that reason I am assuming q dash, right? So here we can use the concept of density. Because density is always same. If you consider 1 drop of water and 1 liter of water, density will always be same. That means if I consider the bigger sphere, that is charged sphere, or the smaller sphere constituting Gaussian surface, that will also have the same charge density. So q dash by 4 by 3 pi is small r cube. Q dash charge enclosed and the denominator is representing the volume of Gaussian surface. Q, charge enclosed, total charge divided by volume of the sphere. So this is representing density of a smaller sphere, density of bigger sphere. Simplifying, we get Q dash is equal to R cube by R cube Q times. Applying Gauss theorem, A dot ds is equal to R cube by R cube Q by epsilon naught. Integrating ds, we get 4 pi R square, R cube by R cube, Q by epsilon naught, R cube and R square gets cancelled out. E is equal to Q by 4 pi epsilon R cube into smaller. Here it is seen that electric field is directly proportional to R. Now we are plotting the graph between electric field versus distance. What we are getting? At the center of the sphere, we are getting electric field to be 0. Now moving away from the center, electric field is increasing linearly, as inside electric field is directly proportional to R. Now on the surface, the value of electric field is maximum, right? That is the maximum as well as constant. Then beyond the surface, if I go, then electric field starts reducing at a rate of 1 by R square, which is shown in the case number 1. Thank you. If you have any doubt, you can ask me. Thank you.